Troubleshooting ground faults can be both challenging and dangerous. Understanding how to properly insulation resistance test is key in order to be able to do so safely and effectively. You need to know the hazards and how to mitigate them, how to set up and use your tool, and how to interpret the results. Let's go to the field, and Brian's going to show us how it's done on a string inverter.
We've got an AC disconnect here. These two inverters are paralleled on that disconnect, so it'll shut them off. But before you do that, if you notice here, the strings are coming into these bulkhead plug connectors. We're not going to need to get inside the inverter to do this testing. I am going to need to open these non-load break rated plug connectors. So before I shut things down, I'm just going to take my meter and make sure I'm actually getting a reading of DC current. 14 amps coming in. All right, so let's go ahead and throw this switch off. Inverters will shut down right away. I'm going to go ahead and lock this out and tag it out just so it doesn't inadvertently get turned back on while we're doing this testing here. Again, I'm not getting inside the inverter. I'm not getting inside the switch. We don't need to verify a lack of voltage. Inverter went off. Pretty sure the AC voltage is gone. What we are going to do though is go ahead and check current on these strings here to make sure that we can safely open these plug connectors. There shouldn't be any current. If there is, we got another problem beyond what we're looking for here. So nothing, 0 amps, 0 amps. Again, each one of these inputs is two strings in parallel. Doesn't really matter though. We're just looking for 0 current here so we can move forward with the testing. Everything looks good on inverter 1. Go over here to inverter 2. Same thing. And you could be like, okay, hey, you're testing positive and negative. It's a circuit. Why do you need to test both? I don't know if these things are wired correctly. I don't really know what's going on inside of them. There's no reason to trust what's here. And it doesn't take much longer to just check all of these inputs. Everything's off, we're looking good. All right, well, we've got no current on our DC inputs, so we can go ahead and undo these non-load break rated plug connectors. You'll notice I'm wearing insulated gloves and leathers here. These are touch-safe connectors, allegedly. They've been out here for over a decade. I don't know who put them together to begin with. I'm gonna play it safe and wear PPE as if there was a shock hazard here. So we're just going to go ahead and disconnect these and then move on to insulation resistance testing them. All right, we've got our string conductors isolated from the inverter here. The plug connects are open. We're going to move on and perform the insulation resistance testing. A couple things to be aware of. Don't make assumptions. These wires, they're white, right? Well, if you get up and look at them real close, you can see the parts that weren't exposed to the sun. There's a little bit of red left on them still. So they used to all be red. It's all faded to white. So those are our positive string home runs here. Another thing we want to be aware of, our insulation resistance tester. If we provide a high resistance circuit by making a bad connection, we're going to get what looks like a really good value, but it's a bad test. So in the case of this particular setup, I want to keep in mind, we're going to be checking these PV strings. So we're going to go positive from the meter to negative of the string, negative of the meter to ground. All right, so at ground, where do I pick it up? Well, if we go back around the back side of this inverter mounting structure here, I've got a ground wire coming up and it's running along the side here and looks like it goes into this gutter and then on into the inverters. It's been outside. It's corroded a little bit looking. It's not very shiny. I want to make sure I kind of cut through that and make a good low resistance connection. Otherwise, we'll get values that look higher than they really are. So I'm going to make that connection back here with this alligator clip and just make sure that that is a really good low resistance connection there. Now on the front side, because we're working with plug connectors, we're going to have to do something a little different. I don't really have a good way to jam something in there. So I'm actually going to use a mating connector. The pins have been modified so it's easy to unplug and plug back in. And then I'm going to take my alligator clip and actually connect to that live end there. So once again, PPE on. We're going to be bringing string voltage out here to facilitate the testing, but that does mean we've got a shock hazard kind of right in our face, essentially. This system's 1,000 volts. So following the IEC standard, we're going to apply 1,000 volts to it. And we want to be consistent in our testing as well. So I've got an off-screen assistant here who's going to be running a timer to make sure that we are performing the test for the same duration from one string to the next. Now, in some cases, we might quickly peg out our meter. First thing you think of is, do I have a bad connection? If not, well, then we don't need to keep testing. If my meter pegs out immediately or quickly, once I hit that maximum value, I'm done. Otherwise, I'm just chewing up batteries. Otherwise, we want to be consistent to be able to make comparisons from one string to the next. All right, so we've got our insulation resistance tester here. We're going to go ahead and perform this at 1,000 volts, as I said already. So we'll go ahead and get that set up. This one has a lock function, so I can hit that, and then hit the test button, and it'll just run the test for as long as I want it to. Again, we're about to bring the voltage outside of the wire, right to that test end there, so want to be careful and make sure we have the right PPE on. Go ahead and connect that together and hook my positive from the meter to the negative of the string. We've got our ground connection around back there. And now I can go ahead and do this test. All right, well, quickly jumped up over 110 mega ohms. It's rising a little more slowly now. In general, we look for a 1-minute test duration. Again, consistency is the key here. It's slowing down a little bit. We're up over 130 mega ohms though. The IEC standard says 1 mega ohm is a passing value. It's a lot lower than what we have here. A lot of what we're going to look for though too is not just is it an absolute pass or fail, we want to look for consistency from one test to the next, which can help us identify outliers that may have issues with them. So it's slowing down now, and we're at about 145 mega ohms. At this point, it's not going to get much higher. There we are, indication the test has been completed. And we'll go ahead and stop the test. Now, remember, this thing's putting current into the circuit. I don't want to just yank this lead off. I might get a little bit of an arc, so we actually stop the test. Now it's safe to disconnect, and we can move on to the next string. All right, next string, we're on string 2 here. Same testing procedure. We're using that lead, making the connection positive of the meter to the negative of the string. The ground connection stays in the same place. Same test voltage, same duration. Let's go ahead and run it. Again, pretty quickly, up over 110 mega ohms. Starts to rise a little more slowly after that as we pressurize that wire with electrons. This is a clear passing value, well above the IEC standard of 1 mega ohm. But again, we want to make comparisons from one string to the other to see where we might have issues. We might flag those for the future. If we start throwing ground faults here, we're slowing down a little bit, 146, 147 mega ohms. That's plenty of insulation resistance. And we should be nearing the end of our test duration, and we're going to call that good, 150 mega ohms. Let's go ahead and stop that test before we pull the lead off, and then we can go ahead and conduct the test on the third and final string for this inverter. We're making our third and final connection here. Everything's going to be performed the same voltage, same connections, positive to negative, negative to ground, 1,000 volt test voltage. And let's test this final string and see what we get. Oh, interesting. This one is not really rising much at all. It went up to 5.5 mega ohms and really has kind of stopped. 5.8, 5.9. Now that's a passing value based on the IEC standard, but it's 20 to 30 times lower than these other strings. So there's definitely a difference in the insulation quality from this one to the other ones. It's a passing value. The inverter hasn't been giving us ground faults, but if it does, well, string 3 here is where I'm going to start looking because it is the one that is a lot lower than all of the others. So it looks like it's kind of slowing down. We're at 6.7 mega ohms. Compared to those other ones that were pushing, what, 150 thereabouts. So that's a significant difference. We'll let this one run for the full duration because it is so much lower, just to see if anything's going on. And yeah, not even going to hit 7 mega ohms on this one. So we're going to definitely flag this one in our records. Not something we need to take offline. The inverter hadn't been faulting, but this is the one that's probably going to cause problems down the road. Visit solartechcollective.com for more information on our consulting and training services, and click subscribe for more videos like this one.